Okay, so in the homework, let's look at a couple of these that you had for last night. I hope you had a nice break. Did you have a nice break? All right. So number two and number 9 are the ones that had slightly lower success, but the overall success on the homework was good. But it's good to start off with stuff we've already done. Get warmed up. So here's a sample. So there's some population. We took a sample of size, what, 36? Let me make that bigger. Okay, so we had a sample size 36, and we got the sample mean to be 24, which would be our what? Our point estimate for the population mean, right? That'd be our best guess of what the population mean is, and that's what this is all about. It's like we take a sample and we're trying to infer about the population from the sample, right? So our best guess at the population mean would be 24. So we have a pretty good size sample, 36. The population standard deviation is 2. We want a confidence level of 95%. So we want to use the one mean z interval procedure to find a confidence interval for the mean population, which from the sample that was drawn. So we're going to make a confidence interval. And this confidence interval is 95%. And so what did we say the z-scores were for 95%? Plus or minus 1.96. But we're going to use the sampling distribution standard deviation. We're not going to use 2. We're going to use what? So our sampling distribution would be our point estimate at the population, right? The population, and then what is our we're using z interval, okay? And so then what is that going to be? Done this a lot. What will the sampling standard deviation be for building our confidence interval? Everyone should know this.
2 divided by the square root of 36.
He wants 2 divided by the square root of 36. You should all have been thinking that, right? And so I think that's 1/3, right? 2/6 is 1/3. So we're going to go 1.96 standard deviations of 1.96 of these up from 24, and 1.96 of these down from 24, and that'll be our confidence interval. So we'll have 24 plus 1.96 times 1/3. So we're going up 1.96 of these standard deviations, and then we're going to go down 1.96 of those. Anyone got a calculator? Crank those out. And they want it to 1 decimal place. As soon as you get it, shout it out. As soon as you get it, shout it out.
24.65.
24.7, okay.
And 23.3.
Does someone else get that? Someone else got that. Great, okay. And so then we'll go over here. Check. Good job. Just got it. Okay, so and maybe this was where the confusion was. It says obtain the margin of error by taking half the length of the confidence interval. So remember that our confidence interval looks like this. And here's our 24. And here's our 24.7. And here's our 23.3. This is the confidence interval from 23.3 to 24.7. We're 95% confident that the population mean lies in that interval. That's the whole point of that. That our point estimate for the population mean is 24, and we're 95% confident that the population mean falls in this range, right? Okay, so it says obtain the margin of error by taking half the length of the interval, so that's this. But then the question is, they kind of worded it weirdly. So they said obtain the margin of error, but then they say what is the length of the confidence interval? So this is the question that they're asking. Is this the margin of error?
No.
Okay, so this may cause some confusion. So they should have said you would obtain the margin of error by doing this. Now, what is the length of the so it seems like it's asking two different things there. So we'll go with the second thing. What is the length of the confidence interval? Is that the same as E? No, the length of the confidence interval is this whole thing. So it'd be 2E, right? So this equals 2 times E. The question they're asking is the full length of the confidence interval, which would be 2 times E. Is that 1.4? Got it. So remember, then there's two ways to do this. Now they're going to have a so that would mean that E is what? 0.7. So now they're going to have us find E that other way, right? That other way, which is basically this thing right here, right? This Z alpha over 2 is our 1.96. Sigma is our 2. So this right here is what we've already done to build the confidence interval, right? It's how far we went up from E, or from the point estimate, and how far we went down from the point estimate. Well, that's E, right? That's half the confidence interval. So that matches perfectly, right? This is our Z alpha over 2, and then this is our 2 over radical 36. So what was the Z of alpha over 2? That was the 1.96. And then the margin of error would be that 1.96 times the 1/3. We already did it, right? It's how far we went up from 24.7. Okay, questions on this one? Any questions on that last problem? There we go. Are we good? Okay, so number 9. So I also go over this because everything it's all building. Everything we do is going to use stuff from before. So you can't just get the homework right and then kind of forget about that stuff and say, I'll work on the next stuff. Everything's building. Like the stuff we do today is going to use this stuff.
What confuses you is when in B it asks you to obtain the margin of error by taking half the length of the confidence interval. And then it asks you right after that, what is the length of the confidence interval? So you're looking at B because that's the question it's asking. And then it hits you with that curveball going, well, what's the length of the confidence interval?
Right. Yeah, that's what I said. You must have been somewhere else. Exactly, right. Okay. Other questions? Okay, this one. So this one also had a slightly lower success, but all right. 95% confidence interval, 19 months, 47 following duration of imprisonment. So here they're giving us the confidence interval. They're telling us that it's from 47.6, 19 to 47.6. for mean duration of imprisonment. Okay, so how would we find the margin of error? There's actually something that would be more important to know before the margin of error. So what would we want to know first? Well, we have the confidence interval. What is this all about? Yeah, so the confidence interval is about, having a point estimate and then having an interval of a certain percent of confidence that we are in that interval. So what could you do? You could do the average of these two, right? Do the average of these two, or you could find this. We could find E first and then add it to 19. So there'd be different ways to do it. And what did you get for that? Did you get the 28.6? That's not right. That sounds better. 33.3. Months. Okay, so the mean, so it's like we took the sample and we got a mean of 33.3, and that was our point estimate for the population mean, and then they built a 95% confidence interval for that population mean. Okay, of the number of months, duration of months for imprisonment. Okay, determine the margin of error. So what is the margin of error? Margin of error would be, you could find that length and take half of it, or you could take this 47.6 minus 33.3. Any way you can get how far of a change it is from 33.3 out to 47.6. And is that 14.3? 14.3. Okay, so we're interpreting this now. What could we say? We can be 95% confident that the minimum error in estimating, sorry, I have to erase now. So on part A, maximum error, that the interval contains the mean duration. One can be 95% confident that the interval from 19 to 47.6 contains the mean duration of imprisonment of prisoners. That's what we want. Right? That's exactly what the confidence interval means. We're 95% sure that the population mean lies in the interval. Oh, boom. That the interval 19 contains the mean duration of imprisonment. Why is that wrong, though? Why is C wrong?
I don't know. I think the answer was B.
But no, we want to understand it. It's not about, just get B and move on. Why is C wrong? One can be 95% confident that the interval 19 to 46 months contains the mean duration of imprisonment. It's a 95% confidence interval. One can be 95% confident that the minimum error made in estimating mu by x bar is found. The maximum error, well, that's true too. It seems like both B and C are true. So B, one can be 95% confident that the maximum error made was the margin of error, 14.3. But I think C says the same thing. So, yeah, I get it if you were confused. I think C is correct. Anyone, last chance, anyone see why C is incorrect? I don't see why it's incorrect. But B is also correct, because when we talk about a margin of error, that's like the maximum, right? So E is the maximum distance we could be from our point estimate and still be within our level of confidence, right? So we can go as far out as this 14.3 months and still be within the 95% certainty level. So my opinion is that B and C are both correct answers. Okay, so the required sample size to have a margin of error of 13 months with a 99. So this is that formula that I gave you in class. What was it? So E is Z times square root of N. So what would N be? N would be Z sigma over E all squared. Is that the formula I gave you? Okay, so this is the required sample size to have a margin of error of 13. So we're going to put 13 there. 99% confidence means 2, that doesn't sound right. 2 point, what's our 99% Z value?
5.8.
I don't think it's 2.58. Is it? Okay, sorry, you're right. That just didn't ring a bell. 2.575. Okay, and then sigma is going to be the same sigma. Do we have sigma?
They give it to you on
There it is, 42. Thank you. So let's crank that out. 2.575 times 42 over 13. Quantity squared would mean this is the minimum size we'd have margin of error of 13 months and 99% confidence. So do 2.75 times 42 divided by 13, then square that. As soon as you get it, shout it out. Okay?
Why would you use like 2.576 or 2.58?
For what? There we are. That's our Z value.
Does it make a difference if you're off by like?
Well, this is more accurate, so we can round at the end. So if we round now, we might get an answer that's. It's better to keep more precision as you're calculating, and then round at the end. It probably won't make a difference, but the possibility is that if we round to 2.58 now, and then we do all these other calculations, then our answer would be too far from the correct answer. Does that make sense? It'll take us off. So we use a more exact answer along the way, and then round at the end. You're still not satisfied.
Well, on the sheet of paper it says that the thing is 2.576, but would it make a difference if you did 2.575?
Oh, I didn't. So I just wrote it down wrong then. Yes, 2.576. Then yes. I just wrote it. I just misheard you guys. Does that answer it?
Yep.
Okay. So what do we get when we do all that?
69.21.
69. Okay, so this is a number. So now this is an n value, right? This is how many in the sample. So if it's 69.21, then how many in the sample is gonna go? What sample size is going to guarantee this 99% confidence for this margin of error? 69? You need 70, right? 69 isn't going to do it. 69 is not going to quite get you that percent of confidence, because 69.21 is this kind of exact value, but 69 won't give. It will be a little bit. You'll be a little bit less confident at 69. So you're going to be 70. Okay, and then build the 99% confidence interval. We'll skip that. So any questions on this one? Last chance. Okay. So the next, we're going to move on to chapter 9, which is hypothesis test. A lot of what we do from here on out is going to be these hypothesis tests. And so this is a really important aspect of statistics, and it's one of my favorite subjects. I like it, so I hope you like it too. Okay, so let's just talk about the general idea, the nature of it. So in hypothesis testing, you have what's called the null hypothesis. The null hypothesis. What is a hypothesis? So first of all, what is a hypothesis? What does that mean? Anyone just give a general idea of what a hypothesis is? Not quite.
It's something that's true. It's a statement that's true.
No, not necessarily.
Educated guess, or
Yeah, so you were kind of on the right track. It sounded like you were saying an estimated value. Yeah, okay. Yeah, so a hypothesis is kind of like, this is what we think is true. It's like, it's our conjecture. It's like, we're wondering if this is true. We're not quite sure, but we're going to see, so we're going to test to see if something is true or not. Okay, so the null hypothesis is something to be tested. Okay, it's just like this, it's a theory or a conjecture to be tested. And so H0, this is important, H naught, this is H naught. Where am I? H naught represents the null hypothesis. Okay? And we'll see an example of this in a second. Lots of examples. Okay? And then there's the null hypothesis, and then there's an alternate hypothesis, and that's H sub A. Okay, don't copy word for word and not listen, okay? Make sure you're listening first and foremost. The alternate hypothesis is we use the symbol H sub A, and so then this is like the alternate to the null. So if we reject the null hypothesis, we reject it in favor of this alternate hypothesis, okay? So we say, no, our null hypothesis, we say we reject that, and we say we favor the alternate hypothesis. Okay, and so then a hypothesis test is we're deciding whether the null hypothesis should be rejected in favor of an alternate hypothesis. And this is kind of interesting because it's kind of not what you expect. So we're deciding whether the null hypothesis should be rejected in favor of an alternate. This is what the hypothesis test is not. It is not to say we accept the null hypothesis. It's either we reject it or we do not reject it. So it's like with these hypothesis tests, all we're doing is either rejecting the null hypothesis or kind of ruling out rejecting it. We don't accept it. We don't say, oh, we never say the null hypothesis is true. We say it might be true, or we reject it. So the hypothesis test is to reject or not to reject. That is the question. To reject or not to reject. That is the question. And this, not to reject, is not the same thing as saying the null hypothesis is true. All it's saying is it might be true. So this is just to say the null hypothesis could very well be true. But we're not saying a conclusion of these tests is never the null hypothesis is true. We never conclude that. All we say that the best we can do is we don't reject the null hypothesis. It might be true. It might be true. Or it could very well be true. Okay, so that's really important. Questions on that, on the premise of these hypothesis tests? Okay, so here's just a little example we'll look at today. For instance, in pretzel packaging, so there's this pretzel packaging example, which we'll see in a second. says the mean weight of all bags of pretzels packaged equals the advertised weight of 454 grams. The alternate hypothesis would be the mean weight of all bags of pretzels differs from 454 grams. Okay, so what is the question, the hypothesis test? The question is, yeah, their pretzels might or may have a mean weight of 454, or we reject that and say, no, there's significant evidence to say that the mean weight in their bags is not 454. Okay, that would be how the hypothesis test would go, and we're going to work on this example. Anybody have a question? Okay, so our hypothesis is going to concern, we've been all about the population mean, so that's what our tests are going to be about, our hypothesis test, about the population mean. Just like our confidence intervals were all about figuring out what the population mean was. Okay, so the null hypothesis, H sub naught, I said H naught. So a null hypothesis will be that the population mean is such and such, is some value. That will be our null hypothesis. Population mean is such and such value. Okay, an alternate hypothesis then. There's 3 possible alternate hypotheses. So there's 3 different tests that we could possibly do. The first one is that, so we say, if we're rejecting the null, we're saying that the population mean is different from the chosen population mean. And how could it be different? There's 2 ways it could be different. What are the 2 ways that the mean could be different from a starting? So here's our mu naught. So how could the mean be different? There's 2 ways it could be different. Too much bigger or too much smaller. Okay, so this is the idea of, again, like an interval, right? This is like confidence interval. And so that would be, we would reject if we were at least this much bigger than the this mu naught, and we'd also reject out here. So this is called a two-tailed test, because if our population mean, if we come up with an estimate for the population mean that's too much bigger than mu naught or too much smaller than mu naught, then we reject. We reject the null hypothesis that mu equals mu naught. Okay, so then another potential test would be this one. The population mean is less than our hypothesized mean. So that's strict, so that's a left-tailed test. So what does that look like? So all we care about is we have our hypothesized mean here, and then our results take us, if our results take us there, then we are going to reject. It's too low. It's the actual mean, we think, we have significant evidence to say that the mean is not mu naught because it's enough less than mu naught. And then there's a right-tailed test, which is the opposite. So if the population mean is more than mu naught. So here's our hypothesized mean, but our evidence shows that the mean is significantly higher than the hypothesized mean. That's called a right-tailed test. And we're going to reject the null hypothesis if the evidence shows that the population mean is a certain degree higher than our hypothesized mean. So whenever you're doing, it's going to be one of these three, right? So you're going to have always have the null hypothesis of some hypothesized mean, and then you're going to have one of these three. You're either going to be doing a two-tailed test or a left-tailed test or a right-tailed test, and you have to infer that from reading the problem, right? It's infer that from reading the problem. Okay, so this is kind of the setup. It'll hopefully make a little more sense when we get to some examples. But does that, any questions, or does that generally make sense? Okay, so let's do some examples here. So here's that pretzel example. Snack food company produces pretzels, and they put on their bag, they say 454 grams on their bag. Okay, so does that mean that every bag has exactly 454 grams pretzels in it, right? No, those are samples, right? Those are each bag is a sample, and we said that there's going to be deviation, right? There's going to be variation to the actual number of grams in each bag, and so that brings the question: if there's deviation, then that raises the question: can they really claim it's 454 grams, or is it something different? Okay. So although the actual net weights deviate slightly from 454 and vary from one bag to another, the company insists that the mean weight of their bags is 454. As part of its program, they periodically perform a hypothesis test to decide whether the packaging machine is working properly. That is to decide whether the mean net weight of all bags is 454. Okay, so what is the null hypothesis? We'll do this one together. The null hypothesis is H naught, and then you do a colon, and we say the null hypothesis is that the population mean equals what? 454. There's our null hypothesis. Okay, alternate hypothesis. Now we have three choices, right? So we got a H sub A, and it's either going to be the two-tailed test, the left-tailed, or the right-tailed. Now, to figure out if it's left or right-tailed, there has to be something in here about saying something like, we want to know if it's significantly lower, or we want to know if it's significantly higher. If it doesn't say anything like that, then you're basically looking at the two-tailed test. You're saying, just is it different than 454? So do we have anything here indicating that we're worried about the pretzels being, the bags being too low, or specifically too low, or specifically too high? There's nothing in there that says that. So all we are is it's not about that people are complaining that there's not enough pretzels in their bags. It's just that, is the machine working properly? Are we getting significantly close to 454? So the machine, by putting too many pretzels in the bag, that's not good, because that costs the company money. And by not putting enough in, then they're not living up to their word of this, the amount in their bags. So all we're doing here is we're testing the performance of the machine, and the machine could be going wrong either by putting too much mass in the bags or not enough mass in the bags, and so that's a two-tailed test. So then we're going to say the null hypothesis or the alternate would be that mu does not equal 454. And that could be too high or too low. Too high or too low. So is that two-tailed, left-tailed, or right-tailed? Two-tailed. So we're not doing any statistics yet. We're just learning how to set up the test. Okay? So the test says, so our null hypothesis is that the mean weight in bags is 454. The alternate is it's not 454. And that's a two-tailed test. Okay, so why don't you try A, B, and C for your notes, okay, while I hand out your sheets for doing, but this Prices of History books will still be for your notes, okay? Still for your notes. You work on that together, okay? Okay, so this one's not for the sheet. This is for your notes. The ones for your sheet are coming next. So let's do one more for your notes. Okay, hopefully we got it by now. Null hypothesis. You check with the people. Yeah, take one more minute. One more minute. Get this right. Okay, null hypothesis. Population mean equals. That's our null hypothesis. And then we're interested in an alternate of, what's our alternate hypothesis? They're saying greater. Agree with that? So that the actual mean is greater than 78.01. So is that left-tailed or right-tailed? That's right-tailed. Questions on this? Okay, your turn. Same exact, so it's just write out the null, write out the alternate, and then two-tailed, left-tailed, or right-tailed. And so we want to really practice the good notation for these A and B, like I just showed you. Okay, so you got to get that. Be precise in what you write here. You want to be precise in what you write for A and B, just like I did in the last examples. And we're not going to go over these. This is on you. Okay, you can work together, but it's on you. Reject, you get, so there could be an error. There could be an error. This is all based on confidence level, right? So it's all based on, it's not exact science. It's based, we talked about confidence intervals. And so we're just examining the evidence, right? So we can make errors in our conclusions in these hypothesis tests. Okay? So this is, you don't want to write this word for word. You want to listen and understand. If the sample data are consistent with a null hypothesis, we do not reject, right? We say it very well could be true that the population mean is that mean that we thought it was. If the sample data are inconsistent with the null hypothesis and supportive of the alternate, then we reject the null. Okay, then we reject the null in favor of the alternate. But we could either reject or not reject incorrectly. It's possible to that we do that incorrectly. So that results in two types of errors. This you want to write down, and you have to memorize what a type 1 error is and what a type 2 error is. You just have to memorize this. So the type 1 error is when we rejected the, I'm going to change this. This is not well worded. Rejecting the null hypothesis when we shouldn't have. Because we don't say it's true. So we shouldn't have rejected. We should have said do not reject. It's possible that the population mean is this mean that we thought, but we rejected because of the sample that we got. Because of the particular sample we got, we rejected, and we shouldn't have rejected. Okay, that's type 1 error. Okay, then type 2 error is not rejecting when we should have rejected. Okay, so we should have rejected the null hypothesis, but our conclusion from the sample that we got was to not reject it, and that's a type 2 error. So I think this chart is helpful here. So here in the columns is if the null hypothesis is quote unquote true or false, and then our decision whether we did not reject or rejected. So if the null hypothesis is true or in the realm of possibility, and we did not reject, then we made a correct decision. But if the null hypothesis was true and we rejected, then we made a type 1 error. If the null hypothesis is false, but we did not reject because of the sample we got, we made a type 2 error. But if the null hypothesis is false and we rejected, then we made a correct decision. So I think that's a helpful table there. And you just have to memorize what a type 1 error is and what a type 2 error is. There's no way around that. So whatever mnemonic device or whatever little trick helps you to remember what type 1 is and what type 2 is, use it. Okay, does this make sense, what we're talking about here? Can we go on? Can we go on? We're good? Okay, so back to the pretzels. Okay, so the null hypothesis was that the bags is working properly and giving weights of 454. The alternative hypothesis is that the mean weights of bags is not 454. Okay, so now in the context, explain what each would mean. So you're talking about pretzels, okay? You're talking about pretzels when you're explaining what a type 1 error would be for this problem. And what a type 2 error would be, you're talking about pretzels. And what a correct decision would be, your answers, so what you say for these answers, it's going to be talking about pretzels. So we know what a type 1 error is. It's when the null hypothesis shouldn't have been rejected, it's true, and we rejected it. Okay, so what would that mean in the pretzel situation, etc. So just practice talking through that with the person next to you. So what do each of these mean in terms of pretzels? Go.
It's like when we say it's wrong, it's actually right. Yeah, because the gene's doing what it's supposed to do. Like it's actually
Okay, so type 1 error is when what? When the null is, for lack of better explanation, the null is true or false?
True.
True, but we rejected. We made an error, right? We shouldn't have rejected. We shouldn't have rejected, but we did based on the evidence, okay? So the evidence was like an outlying evidence, right? It is a sample that wasn't representative, right? It was a sample that wasn't representative of the population necessarily, and so we came to this wrong conclusion. The null is true, we rejected. So what would that mean for pretzels in this situation? What can you restate that for this particular context? A type 1 error, what would it be? I'll try.
I guess the possibility of there being 454 grams of pretzels was rejected wrongly.
Okay, so he said that there's 454 grams per bag, or the mean weight of bags was, she said, was rejected wrongly. So what does that mean?
That the machine is correctly dispensing 454 grams of pretzels.
Right.
When we think it's not doing that.
That's it. Yeah. So the machine is doing its job according to our null hypothesis, but we said it's not. We said the machine is faulty. That would be type 1 error. Okay, type 2 error. What would that be? Somebody new? Okay, null is false, but we did not reject it, but it's false. So what would that mean for the pretzels and the machine? Could you restate that in terms of the pretzels and the machine? We think it's giving us the right amount, but it's actually not. Is that a type 2 error? So the machine is actually not doing its job, but we concluded that the machine is okay. Is that right? Is that type 2 error? Yeah, she got it. That was it. Yeah. The machine, so now the machine is faulty. It's either the population of these, the mean grams per bag is either too much or too little, far away from 454. But our conclusion from doing the test was that the machine's okay. It's doing its job. And that'd be a type 2 error. Okay, then there's 2 ways to have a correct decision. Did you come up with that? There's not just one way. There's 2 ways to come up with a correct decision. What's that?
Yes. It's like
Tell me. Tell me one of them.
if the pretzels, if the packages were doing all the packages were coming at 454 and we didn't change the machine.
And we didn't what?
We did not change the machine if it was correct.
Okay, so first of all, are all the bags coming, is that where we said we're,
But
yeah, they're going to deviate. They're going to deviate.
but there's not enough difference to change it.
Okay. So yeah, so the machine is working properly, and we concluded as such that we did not reject the null. We said that the mean very well could be 454. Or the machine is truly not doing its job, and we rejected the null, and we said that the mean weight of the bags is not 454. Those would be the correct decisions. I think we've already kind of talked about D&E. Oh, no, okay, so this is just practice here. So, yeah, do D&E on your own. Go, do D&E. So,
Notes are on the paper.
just notes. So we're rejecting, okay? So we carried out the test and we rejected. The conclusion is that the mean weight of bags is not 454. So classify it as a correct decision or type 1 or type 2 error, D and E. So our conclusion was reject. So D, if the mean weight is in fact 454 or something really close to that, then is it correct or do we commit an error? It's an error. What kind of error is that? I heard both. So some people are saying type 1, some people are saying type 2. So the mean weight is in fact 454, but we rejected. We said the machine is not working properly. Type 1 or 2? That's type 1 error. That's type 1 error. You agree with that? Some people said 2. I just want to make sure. Okay. What about if the mean weight is in fact not 454 and we rejected the null? Correct decision. Right? So we said the machine's not working properly when in fact it's not working properly. Any questions on the type 1 and type 2 errors? Okay. Your turn. Now I'm going to... So the test, I'm going to write out the test over here. So the test is to decide if females under 51 and we're just going to do the first one, okay, for time's sake. Just going to do 9.23 on your sheet. The test was to determine if females under 51 are getting less than 18 milligrams of iron. Go back to your notes. Go back to your notes. What is the null hypothesis? What are possible alternative hypotheses? So let's do that too. So before you start this problem, so that we're all on the right track, do this first. What's the null hypothesis? What's the alternative? The null hypothesis is we only talked about one kind of null hypothesis, and then there's 3 possibilities for the alternative. So make sure you have that before you start. Last chance. Okay, we're going to press on. Last chance. Okay, so let's talk about significance level. So the probability of making a type 1 error, that is of rejecting the true null hypothesis, is called the significance level. And we've seen this alpha before, and now we're going to see what it means, right? So we've been dealing with this number, this symbol alpha, number Z alpha. Well, now we're going to see that this it had to do with hypothesis testing. So, in that last one that you just did, was it a right or left-tailed test? Left-tailed, right? So our rejection region would be here. And what was alpha? Alpha was an area, right? An area, so this case, that right there, that area right there is alpha. Okay? And so if this is not, so that area then is also the percentage or the probability of making a type 1 error. So it would be that we should not reject, right? We should not reject, but we did. So there's that probability. It's the probability of making a type 1 error. Does that make sense? So in the case where we should not reject, but we do, then we ended up with evidence that landed us with a z-score over here, and there would be a whatever 5%, say at the 5%. If alpha was 0.05, that would be a 5% chance that we end up with a z-score in this region. And if we shouldn't have rejected, we're going to reject over here. We're going to reject because we're significantly lower. But if we shouldn't have rejected, then that's that percent chance that we're going to reject. We're going to end up with a z-score over here when we shouldn't have. So it's a probability of making a type 1 error. And that's called the significance level. Okay, the type 2 error occurs if the false null hypothesis is not rejected, and the probability of that happening is denoted beta. But alpha is the more important one. The probability of making a type 1 error is alpha. And it's the same alpha that we dealt with before when we didn't really have a meaning attached to it, except for it was a area under the curve or a probability. Okay. Good on this slide? All right, so let's talk about, can Jack hit his tee shot an average of 275 yards? So Jack is claiming to his friend, I can hit the ball. I hit the ball on average 275 yards, my tee shots. And so he hits 25 drives and got a sample mean of 264 and a sample standard deviation and population standard deviation of 20. Okay, so first let's set up the test. So what is the null hypothesis? So should this be 275 or 264.4? The null hypothesis. Can Jack, so Jack is claiming he can hit his tee shot 275. He hits 25 drives and gets that sample mean. So is our null hypothesis that he can hit it 264.4 yards on the average? No, we already know he can do that. He just did it, right? We know he can do it 264. What we don't know or not is what? 275. That's what he's claiming. So this is our null hypothesis is that he hits his drives an average of 275 yards. And the alternate is that? Less, right? So So this would imply like he's claiming he can hit it this far. So the alternate would be no, he doesn't hit it that far. So less than 275.
So if it was greater than 275, would still count because he hit at least 275?
We're just deciding, we decide what kind of test we're doing, right? So this test is the left-tailed test, where we're saying that we're going to reject. Yeah, so if his true mean is greater than 275, then that claim is fine, right? Does that make sense? Yeah, but it's when if he's hitting it significantly lower than 275 that we have a problem with his claim, right? So at the 5% significance level, alpha is 0.05. We have a 5% chance of a type 1 error. Okay? So here's our 275. So we want, at the 5% significance level, this area over here is going to be 0.05, and that's alpha. Okay, and so what is the z-score for that? What is the z-score for 0.05? Who's got their chart? 0.05 to the left. So z of 0.05 is what?
Oh.
1.645? So now we're going to figure out what he did in his sample, and we're going to compare it to that 1.645. So what did he do in his sample? He hit it 264, population standard deviation 20. So we are going to look at, so our point estimate for his average is 264.4. And we're going to look at, to get the sampling distribution, sampling standard deviation, it's going to be the 20 divided by, how many did he hit? 25. So it's going to be 20 over 5, or 4. Oh, sorry. This is, so we're considering we're considering 275. And we want the z-score for 264. So right, so we're saying what z-score is going to match up with 264. So we're going to go, what, 264.4 minus 275 all over 4. And by the way, this should be negative 1.645, right? Because we're to the left. So what is the z-score according to his sample? What's the z-score for his sample, 264.4? You do 264.4 minus 275 over 4. And you get negative 2.65. So if his mean is 275 and he hits a sample 264.4, that is 2.65 standard deviations below the mean. Where is that on here? Is it in our rejection region or in our non-reject region? It's over here, right? And it's bad, really bad. It's like a whole standard deviation lower than this. Do you see that? So for a 5% significance level, the z-score is negative 1.645. That's our breakpoint for not rejecting the null or rejecting the null. And where does his sample come out? Way below that. So his mean of 264.4 is like 2.5 standard deviations below 275. And so what about his claim? Are we going to accept his claim or reject his claim? reject big time, right? This mean of 260.4 yards is a lot of evidence to suggest that he does not hit at 275. Our break point for rejecting or accepting was this. That was our break point for accepting or rejecting. His mean of 264.4 suggests a 2.65 standard deviations below, which is well less than our break point. So we are going to reject his claim. Reject the null. And say, we don't think Jack can hit at 275. We don't think he can do that based on the evidence. Now, what we also talked about, there's a 5% chance that we're making a type 1 error. There's a 5% chance that we're making a type 1 error here. By rejecting the null hypothesis at the 5% significance level, there's a chance that that this is just a really low, this particular sample, he just did really badly in this sample. And so there's a 5% chance that we're rejecting incorrectly, type 1 error. Okay, we're going to do lots of this. So if this, I want to just get through one example, but if parts of this didn't make sense, never fear, we're going to do lots of these in practice. You can